Hello, welcome to Q in Motion's course on understanding electricity and electronic devices. This is our fourth class, and before we go on, as usual, let's start with a quick review of what we saw in previous classes. So on the last class, we studied Kirchhoff's laws, and we studied that there are two laws, one relating to voltage and another one relating to current. We also studied LEDs and that they have a specific polarity, and you normally want about 10 milliamps flowing through them. They also have a voltage drop that depends on the color. We also had a look at different kinds of switches, different poles and throws, how to specify them. And also on a previous class, we discussed about Ohm's law and resistors. When we studied resistors, we learned that those are specified both with the value and the maximum power that they can handle. And today we're going to be looking at the following. We're going to be looking at resistors in series and parallel. We're going to be looking at configuration of resistors that it's called a voltage divider, and we're going to be looking at a new device, which is variable resistors. And we will also be learning about electric power. Let's start with resistors in series and parallel. We say we have two or more resistors in series when the same current has to flow through all of them. In this example, we have a 5-volt power supply, and current flows from the positive terminal, passing through R1, then R2, then R3, and then going to the negative terminal of the power supply. In this case, whenever we have these resistors in series, the total resistance of the path is simply the calculation of this equation, which is R1 plus R2 plus R3. So you simply sum or add up all the values of the resistors, and that's your equivalent resistance. That's very simple. So let's do a quick example here. Let's calculate the current flowing through this circuit. So we have a 1 kilo ohm resistor in series with a 2.2 kilo ohm resistor in series with a 4.7 kilo ohm resistor. If we add all of these resistors, we end up with an equivalent resistance of 1 plus 2.2 plus 4.7. That would be 7.9 kilo ohms. Okay. Now, if we remember Ohm's law, after we calculate the equivalent resistance, we can calculate the current by applying Ohm's law. In this case, the current is going to be voltage over resistance, or 5 volts divided by 7.9 kilo ohms, and the current through this circuit is going to be 0.63 milliamps if you do the math. Let's now have a look at resistors in parallel. So we say that two or more resistors are in parallel when the current splits in different branches, one per resistor, and then combines back. This is an example that we have here. We have the same 5-volt power supply. Current will flow from the positive terminal all the way up to here, up to this node. And here it will split into parallel branches, R1 and R2. And then the currents will combine here, and then we'll go back to the negative side. When this happens, the equivalent resistance can be calculated as R1 times R2 over R1 plus R2. Keep in mind that in the previous example with the resistors in series, as we add more resistors, the total resistance increases, right? So we're adding more resistance in the path of the current. When we have resistors in parallel and we add another resistor in parallel, we are providing an alternate path for the current to flow. So as we add more resistors in parallel, the total resistance is going to be decreasing. So when we have two resistors in parallel, the total resistance is always less than the lowest of these two resistors. And it, like I said, it can be calculated with this equation. Let's see an example here. Let's calculate the current flowing through this circuit. We have a 5-volt power supply and two resistors in parallel. The values are 2.2 kilo ohms and 1 kilo ohm. So we start by calculating the equivalent resistance, which is R1 times R2 over R1 plus R2. And that is 1K times 2.2K over 1K plus 2.2K. The result of this is 0.687 kilo ohms or 687 ohms. And as you can see, this value is lower than any of these two. And this is something that's going to happen. Now, if we want to calculate the current, we apply Ohm's law. And current is voltage over resistance, and that would be 5 volts over 0.687 kilo ohms. And the result of that is 7.27 milliamps. All right. Now, what we saw in the previous examples were pure series and parallel combinations of resistors. Now, resistors in series and parallel can be actually combined, right? In this case, we have R1 and R2 in parallel. We have R3 and R4 in parallel. And the combination R1, R2 is in series with the combination R3, R4. All right. So if we want to calculate the equivalent resistance of this whole thing, we do this in parts. So because R1 and R2 are in parallel, we can calculate this R12 as the formula for the parallel resistors for R1 and R2. We can do the same for R3 and R4, right? R34 is R3 times R4 over R3 plus R4. And that is the equivalent resistance of this block here. And because this block is in series with this block, we can calculate the overall resistance as the sum of these two, because these two blocks are in series, right? So the equivalent resistance of this whole circuit is going to be R12, which we calculated here, plus R34, which we calculated here. All right, so we saw resistors in series and in parallel, and we're going to be having a look at the voltage divider, which is a specific configuration of resistors. So this is what a voltage divider looks like. So let's calculate VAB, the voltage between the terminals A and B, to have an idea of how this works. First of all, we calculate the current flowing through this one. R1 and R2 are in series, right? So the equivalent resistance is the sum of R1 and R2. And applying Ohm's law, the current I is going to be 5 volts divided by the equivalent resistance, which is R1 plus R2. So the current is the input voltage, 5 volts in this case, divided by R1 plus R2. Now, if we want to calculate the voltage between A and B, we multiply the current, again, Ohm's law, we multiply the current times R2 times this resistance, which is 3.3 kilo ohms. So I times R2, that's the voltage between A and B. And substituting I with this one, with this equation, we get that the voltage between A and B is the input voltage times R2 over R1 plus R2. Okay. if we actually replace the actual values here, the voltage between A and B, it's going to be 5 volts times 3.3 kilo ohms, which is this resistor, over 10 kilo ohms plus 3.3 kilo ohms, which is the sum of these two. And we will end up with 1.24 volts. So this circuit lowered the voltage from 5 volts to 1.24 volts. Let's have a look at the effect of the load in a voltage divider. So we calculated the voltage in this circuit without this resistor here between the points A and B, and we ended up with 1.25 volts. Now let's assume we want to connect this to another circuit, and that circuit is going to be represented by a 100 ohm resistor. So when we do that, really we're changing the circuit because now R2 and R3 are in parallel. And the equivalent resistance of 3.3 kilo ohms in parallel with 100 ohms is 97 ohms. Remember, when you put resistors in parallel, the equivalent resistance is going to be lower than either of the two, right? So if we recalculate the formula for the voltage divider, but now with an equivalent resistance here of 97 ohm instead of the original 3.3 kilo ohms, we see that the voltage between points A and B, it's going to be 0.048, right? So this is much less or much lower than the 1.24 volts that we wanted. So what's the conclusion here? The conclusion is that voltage dividers can only supply very little current. As soon as you try to pull current out of this circuit, the voltage is going to drop even further, right? So let's recalculate this circuit, but let's assume that we have a 100 kilo ohm resistor here instead of the 100 ohm that we previously had. So again, R2 and R3 are in parallel, but the equivalent resistance of this parallel combination is 3.2 kilo ohms. When we recalculate the voltage divider with 10 kilo ohms and 3.2 kilo ohms, we will end up with a voltage between points A and B of 1.21 volts, which is a lot closer to the 1.24 volts. So just remember, voltage dividers can supply little current. So this 100 kilo ohm resistor is pulling very little current from this circuit, and that's why the voltage doesn't drop a lot. It drops very little, from 124 to 121. So this is an application for a voltage divider. Like I said, voltage dividers are not used for power because they cannot supply a high current, but they can be used to interface a higher voltage circuit to a lower voltage circuit. For instance, here we have a 24 volt sensor, which is powered up by its own 24 volt power supply. Then we have a voltage divider here. And it doesn't look exactly like the ones on the previous pages, but it's still a voltage divider. We will get back to this one in a minute. In the other side of the voltage divider, we have a controller that accepts inputs from 0 to 5 volts, and it is powered by its own 5 volt supply. So we're not obtaining 5 volts from these 24 volts because, or not with a voltage divider anyways, because like we said, we cannot use a voltage divider to supply power to another device pretty much because the current is going to be very, very limited. But we can use it to lower the voltage from these 24 volts. This sensor puts 0 or 24 volts. Let's assume it's this sensor is I don't know, detecting it's like a switch. detecting a specific object, right? And this thing is going to be outputting 0 volts when there's no object, or 24 volts when there's an object there. Now this controller only accepts 0 to 5, right? So we're good with the 0, but the 24 volts is too much for this 5 volt input. So we put this voltage divider here. And if you have a look at these two resistors are in series, right? So when we have 24 volts, we have current flowing through this loop. And we're taking the output voltage from this bottom resistor between ground and this middle point. So this circuit, it's drawn with this resistor put horizontally, but it's still the same voltage divider circuit that we saw in the previous slide. If you want to know what are good values to put in these two resistors, for this circuit to lower from 24 to 5, 3.9 kilo ohms and 1 kilo ohm will do the trick. You're welcome to do the calculations, and you should be getting like 4.9 volts over here when you put 24 volts over here. Let's talk about a new device that it's called a variable resistor. A variable resistor can look like this one, or this one. Let's focus on this one first, right? It has 3 terminals, and it has a fixed resistance between 2 of these 3 terminals. So it's going to have a fixed resistance between this point and this point. And then this point can be placed anywhere in between. So if the resistance between this one and this one is, say, 10 kilo ohms, this one, when this knob is in the middle, it will have 5 kilo ohms between this one, and another 5 kilo ohms between this one and the other one. The symbol is this one. So here at the bottom right, so it's represented as a resistor. The resistance between this point and this point is fixed. And this is called a wiper, and it can slide along this resistance. It usually has like a carbon track inside. So this can be placed in any place in the carbon track. So when this is closer to this side, we may have maybe 1 kilo ohm between this point, and 9 kilo ohms between this point and the bottom one. When this is closer to this side, we will have like 1 kilo ohm between this point and the bottom, and 9 kilo ohms between this point and the top. And when this one is in the middle, we would have 5 kilo ohms to one side and 5 kilo ohms to the other side. So they come in different formats. Like this one is rotary, and this one is sliding. And this one is called a trim pot. So this one is, these two are meant to be adjusted or moved by the end user, right? Maybe like a volume control for an audio amplifier. Or this one could be the same thing for an audio mixer or console. And this one is not meant to be adjusted by the user, but it's meant to be adjusted in the factory to adjust, to fine tune some parameter inside the circuit, right? So you would require some tool like a screwdriver to adjust it to a set position, maybe measuring something, some value that you want to adjust, and when you get to that point, you just leave it alone, or maybe you drop, you put a drop of glue in there so it doesn't move accidentally. So all of these have 3 terminals: this one, and this one. Here you can see those clearly. And here you have 1, 2, and 3. This 4th one is connected to the case, and it's for mechanical support only. So sometimes variable resistors are represented as two terminal devices like this one, right? So it would vary the resistance from 0 to a maximum between this point and this point. But really, when you see this, you probably are going to be implementing it like something like this. So you are connecting the middle terminal with one of the ends and taking the resistance between this point and this point. So the way it works is you are short-circuiting part of the resistance here, right? And the only useful part of the variable resistor is from this point where it's making contact until this end. So this is how you can transform a three-terminal variable resistor into a two-terminal variable resistor. Now, if we have a look at this looks a lot like the voltage dividers that we've been studying in the previous slides. So when you have a 5 volt or any other voltage supply here, and you connect that to a variable resistor, you can adjust the variable resistor to obtain any voltage that you want here between 0 and 5 volts. All right, so this may come handy if you are building a variable, an adjustable power supply. You could adjust that to any value you want between 0 and 5 volts in this case. All right, so this may be a good time if you want to take a break. So just hit pause, and when we come back, we will start talking about electric power. So power, what is power? Power is the amount of energy delivered per second. And I know it's not, I don't know if this definition is going to help or not, but this is from a physics point of view, this is the definition of power. Now, energy can take different forms like heat, motion, light, radio waves, sound waves, etc. Electric power delivered to a device is calculated as the voltage times the current flowing through it. So power is measured in watts, and 1 watt is 1 volt times 1 amp. So this is the formula for it. Let's have a look at one quick example. So we have a 3 volt power supply, and it is supplying 2 amps to this device, and we want to know how much power is that. So that's simple enough. Power is voltage times current. That's 3 volts times 2 amps. That's 6 watts delivered to this device. All right. Now, let's do the reverse problem, right? So we have a 120 volt power source. This may be an outlet. And this is connected to a 1200 watt heater, right? So you want to heat something, and the heater is rated 1200 watts. So you want to calculate how much current you're going to be taking from this power supply. So power is voltage times current, so we can solve for current here as power over voltage. So that would be 1200 watts divided by 120 volts. And this is 10 amps. So you have to make sure, if you are going to be powering up a 1200 watt heater, that the cables and the outlet can handle 10 amps to this heater. Okay. So let's calculate the power delivered to a resistor. We can combine the formula for power with Ohm's law. So this is the formula for power. Power is voltage times current, but current in a resistor is voltage over resistance, right? So voltage times voltage is voltage squared, and the power can be calculated as voltage squared over resistance. So if you know a resistor and you know what voltage is applied to it, you can calculate the power delivered to that resistor. Now, in this formula of power equals voltage times current, we can replace voltage. Here we replaced current with voltage over resistance for Ohm's law. But here, if we replace voltage, that's current times resistance. So this is Ohm's law. Voltage is current times resistance times current again to calculate the power. So that is I squared, I times I times R. So the power is going to be I squared times R. So if you have a resistor and you know how much current is flowing through it, you can calculate the power as well. All right. So these are just substitutions that allow us to calculate the power delivered to a resistor easier. So let's see an example of how we do this. So let's calculate the power delivered to a 100 ohm resistor when 5 volts are applied to it. So we have the circuit here, 5 volts, a 100 ohm resistor. Let's calculate the power. So because we know what the voltage is, we use this equation, V squared over R. So that would be 5 times 5 divided by 100 ohms. And when we do this calculation, we end up with 0.25 watts or 250 milliwatts or 1/4 of a watt. We're going to get back to this example, so keep it in mind. 5 volts, 100 ohms, that's 250 milliwatts or 1/4 of a watt. Now let's talk a bit about conservation of power. So energy and therefore power cannot be created or destroyed, only can be converted. And any power delivered to a device that is not converted to useful power, and by useful power, I mean light or motion or whatever it is that you're trying to get out of it. So whatever is not converted to useful power will be converted to heat. So if you have 10 watts delivered to a motor and the motor is putting out 5 watts of motion, of mechanical power, the other 5 watts are being used to heat up the motor. So we want to keep that amount of heat as low as possible for a couple of reasons. First, it is wasted energy that you're not using. And second, heat can damage many devices. So let's go back to a slide that we saw when we studied resistors. So resistors are specified by the resistance in ohms and the maximum power that they can handle. So most small resistors are 1/4 watt or 1/8 of a watt. High power resistors usually have a square body like this one, right? This is a 5 watt resistor. This is 2 watt, these are 2 watts and this is 1 watt. But there are smaller ones that are the most common that are 1/4 of a watt. So resistors do not deliver any useful power output normally, unless you're building a heater. But in a resistor, all energy is converted to heat. And excessive power will burn a resistor. When using a low value resistor of less than 100 ohms in a circuit, right? Assuming we use circuits with lower voltage, like 5 volts or around those values. So on a previous slide, we saw that when we apply 5 volts to a 100 ohm resistor, it's going to be dissipating 1/4 of a watt. And because that's the limit that a small resistor can handle, whenever you have 100 ohm resistors or less, it is a good idea to check the power that you're going to be delivering to it to ensure that you're not exceeding the maximum power. If you're exceeding the maximum power, you would have to use a power resistor like these big ceramic square ones that I was showing here. If you have high value resistors like 1 kilo ohm or higher, you will not be able to exceed the quarter watt in circuits with low voltage, like 5 volts or 10 volts. All right. Let's do a quick review of what is it that we saw today. Today, we studied resistors in series and parallels, right? So we saw how resistors can be connected in series, parallel, or a combination of both. When you add resistors in series, you end up with an overall higher resistance. You're adding up the value of the resistors. When you add resistors in parallel, you end up with an overall lower resistance because you are providing more paths for the current to flow. So the current flows easier. That means lower resistance. Okay. We also studied the voltage divider, which is really two resistors in series, and you take the voltage over one of them, right? It allows you to generate a lower voltage by dividing the input voltage by a factor that depends on the resistance, on the resistors. It can only supply a low amount of current. And one example of use is that you can use it to interface higher voltage circuit to a lower voltage circuit. In the example, we saw how we can interface a circuit that's powered with 24 volts to another circuit that is powered with 5 volts. After that, we had a look at a new device for us that is called a variable resistor that offers a convenient way of producing a voltage divider that is going to be adjustable. So it could be user adjustable or factory adjustable. Then we had a look at electric power, that how we can calculate it. We calculate it as voltage times current. And it's going to be usually delivered as heat, light, motion, or also radio waves or sound waves, for instance. Some devices like resistors have a limit on the power they can dissipate. And we can calculate the power to a resistor based on just the voltage and the value of the resistor, or the current and the value of the resistor. And that's all for today. Next class, we will look at some electromechanical devices. We will look at electricity and magnetism, how they are related. We're going to look at electromagnets, DC motors, relays, and transformers. So that's all for today. Thank you for watching, and see you next class.